IW4BLG to tell us about some of his experiments and information on 10 gigs. He tells me that he was, since he's been a kid, he has been attracted to technical stuff, and even as a child he was a very curious sort of child. I think I know what you mean by that. He built his first crystal radio at the age of 9. Hands up those who can also claim to have done something at about that age. Yeah, you see? You're amongst friends. And repaired his first TV at the age of 14. Who first got a belt off a TV on a live chassis at about that age? Yep, fine. We're all with you. And turned 21 when he became a radio amateur with the call sign IW4BLG. Since then, he's developed a lot of radio gear and fell in love with space communications. I think we can all put our hands up to that one as well. Became an EMEer and a satellite enthusiast. His passion led him to experiment a lot on the higher bands, up to pioneering several terahertz lightwave QSOs in the early 90s. Beside his passion for radio communication and modern technologies, he likes to study, experiment, understand why, and then to write and share to better spread the knowledge. So this has led him to become an author of more than 45 technical articles and to publish 10 science books. I'm not sure we can all put our hands up to any of those. So there you are definitely ahead of us. So welcome, very big welcome to you, and please tell us what you've been up to on 10 gigs.
Okay, thank you very much for everybody. This is my first talk abroad, so I will appreciate your understanding for that. Time is running fast. Let's start. The goal of this talk is not to teach you anything, because I think you probably know even more than me, but just to tell what I did, to try to answer to some question, something that was not clear to me. Why I started this project 2 years ago. In 2009, I was asked by the Tor Vergata University, this is one of the 3 universities we have in Rome, to hold a lecture about amateur satellite in front of the people, the student of the Master Spazio. Master Spazio is a post-degree course for people that want to specialize on space communication. The students are stuffed with formulas, theory, whatever, but nothing real, not iron. And so at the bottom of the course, they reserve a little slot for people that do things in practice. Some company, some amateur, whatever, they really try to transform theory to real gears. And my piece of story there. During my lecture, I presented to them these 2 slides where I say, well, one of the questions you normally do to ourselves is, I'm on a band, I'm a satellite up there, how much signal do I get? Okay, I do some calculation of path loss, but then how exact it is, how much fading I can get on that band. Well, of course, there are data present on some books, some obvious deduction, you can do it, but I never found really data for a specific band, what can be the fading on a specific band on ground to space segment. So I say, well, these data are already known from every company that deal or offer satellite services, but are not published usually because they are very strategical within the company to know exactly these numbers. So I say, well, let's try to have a clue at least what can be the range of this fading. Say, but I have very little budget, very little knowledge. Say, why try to do this analysis by myself? The rough idea is very raw. It is to have a beacon flying and a ground station that is barely a receiver with some data logger. That is a very typical situation. Just I put some transmitter, receiver, and then try to see what happened in between. It's very easy in theory, but where I can find a stable and reliable transmitter on the outer space, that is the second question, because now I have to move to the practical stuff after the theory. I try to write down what I was in need to do these things. I say, I need a stable position in the sky, so I don't have to follow the satellite. because this makes even more complicated calculation and the station and whatever. I would like to have a frequency to record, to do an experiment close to our hand band, so I can probably adapt the result to our band very quickly. Some known unstable frequency, the known unstable output power, stable known footprint, polarization, and last but not least, I need to have a good signal to noise ratio using something easy, something I can have in my home, not a 10-meter dish, of course, or a special receiver. This was the start point. So what was the solution, or at least my own solution? It was the most, or probably all the TV satellites that broadcast the program have one or more beacon on board. And they are delivering signal on 11, 12 gigahertz, so not far from our 10 gigahertz. So why not to try it with that opportunity? The first try was very straight. I had already my roof for watching TV, a dish with LNB for a hot bird. It was answering positively to several questions, but number 3, number 4 was not exactly what I would, because the frequency was stable, but I could not find any specification how much stable it was. I tried also to write several emails to the consultant that lead the satellite. I never got an answer. Okay, and also the power is, I don't know, sometimes the signal it changed suddenly, or it jumped the frequency, the beacon. I don't know what they are doing on that. So, okay, was good, but was not perfect as I would like to have it. So I say, well, let's have a look to other satellite. And for accident, I discovered the Hispasat. They are in middle of Atlantic to cover both Brazil, Argentina, and Spain, Portugal, and Central Europe. They had all what I needed. And the good point also, they declare every details of the satellite over the internet. If you go on the web page, you can download all the specification of every satellite they have on service at the moment, with all the details. That is very nice to read it. So I say, well, that is good. And also I have an extra for free, that this satellite, being so far on the east or west side, is also very low on the horizon at my place. It's just 22 degrees of elevation. So I have a very long path across the atmosphere and outer space, so it probably put even more evidence the fading. Then I say, well, now I have the beacon, I have the receiver, more or less. What else I can try to monitor at my place to make a reasonable guess what can impact on the fading? I say, well, let's say atmospheric pressure, very easy to record. Air temperature, it comes almost for free. Relative or absolute humidity, and the rain or idiometer falling, whatever is snow, hail, or light rain, whatever, fall from the sky in water fall. These are the 4 things I thought at the beginning may impact that I may be able to record. Probably there are more, but I'm not able to check it, so was escaped from the list. The ground station was a dish, regular, it's just 40 centimeter diameter, very little. And this is also good because I have a beam that is 3-4 degrees at that frequency. This means that although maybe the satellite is not very stable, I get no feeding for stability. I have a front end homemade to supply power and tone to the LNB to write frequency and polarization. Then I used an old ECOM, I cannot say SDR, but anyway, a PC-driven receiver. That was the old PCR 100. Then there is a rain gauge, a small Arduino board to transform in something readable to the computer the output of this damn bad sensor. That is quite stupid, but it works, but not so easily. And then I have a computer that collects things all together, drive the receiver, and deliver out in a readable format all the information. The data logger was at the very beginning. I started from an old i386 with DOS and something written in C++, just to have a clue if I was on the right path. It says, well, it works. The idea is good, so let's spend some more money. And I took a Pentium 3 later on, and with the help of a good friend that is very nice in coding, I wrote the algorithm on paper. It's coded in PHP. We prepared all the software to drive the receiver, drive the logger of the signal, and put all the things together. And also publish in real time on my webpage, so I could check if everything was working or stuck from away from home. Once all that was set, what you could get? A long file, a data streaming like that, where I have time, data, the time. Every minute I was cycling and checking signal level, average signal level. This is the index for the algorithm, internal. What is the frequency at that moment of the signal received? Mission time, MT, since the last reboot of the computer. Pressure, temperature, relative humidity, and rainfall rate. Seems very easy, but after 1 year I have more than 500,000 of rows of data on my computer. That is not thing serious, but not so easy. When you try to import such amount of data on a normal spreadsheet, or it crash all the same, then no, I don't want to do it in your elaboration. So I start to look for a software, was for free possible, that could be able to handle such amount of data and also do some calculation, mostly statistical. And I found a QTI plot that is very handy. It's open source software, available on most Linux PC based, and I got started. This is how it looks like. You just import like a text file, and just one click, and it delivers all the statistical data or analysis you want on your row, on your cross and row, very easily and very quick. It's just 1 second or even less for 500,000 rows. After 1 year, what I got? This is the summary sheet of all the variables I collected. This is the first row. I mean, the average is the level received. The very lowest value was minus 22 dBm. In average, was minus 73. The very best case, it was minus 70. This means almost 22 dB of fading in 1 year. This is the frequency. We have to add 10.6 gigahertz as local oscillator within the LMB. That is more or less variable 1.1 megahertz. That is obvious for a DRO oscillator, nothing special, but at least we know. The pressure, atmospheric pressure, well, reasonable. And in full agreement, I have not far from my place, there is an official meteorological station, so I double check it more or less, the spread is, we were aligned. The air temperature from minus 14 and up to 47. This was not the real air temperature, but the temperature of the box of LMB, because I glued the sensor on the bottom of the front end. Relative humidity, that is probably was even worse, the spread in the reality, because it's very foggy in my own area, so probably 84 is the limit of the reading of the sensor. Rainfall, 0, dry days, very dry, but when it's fall, it's fall. 100 millimeter hours is a lot of. I try to plot, for curiosity, what is the drift of the temperature of the local oscillator within the LMB, just for curiosity, you have the frequency, you have the temperature outside. And you can see for area, there are areas where you have this slope that is more or less parallel to that. From time to time, I discovered that the local oscillator jump to another frequency. As a constant temperature factor, but maybe I switch off for 1 day, 2 days. Then when I reactivated the LMB, was shifted a little bit beside. So I get this cloud of point, and after a while, I get this cloud of point. The slope is the same because the thermal coefficient is still the same. And I say, well, it's still the same here, but what about this area? This is a problem due to the fact that I have a lot of fog, and often it was icy during the night. So it was coated of ice, the LMB, a little bit. So the internal temperature was not exactly the real temperature of the oscillator, the one that we were measuring. So I was in some kind blind in this range of temperature, just a few degrees above zero. I could read almost stable temperature while it was not true for the system. And in fact, when it goes to very lower temperature, when it gets dry, and so what is inside is what is outside, then I start to have it again, more or less the same slope. This was out of the target of the experiment, but was coming for free. Just say, let's see if I got reasonable figures or just stupid figures. I got this picture. I say, well, now I must explain what I see in some way. Then the question, I have a lot of data, but who does what? That is the question. What this can be a gauge to understand that was the correlation factor in my mind. Correlation factor is a classical statistical index that can vary from +1, where you have very straight and tight correlation from A and B, and -1, very tight, but one rise, the other one fall. It can be something in between, so some noise or more noise. This is almost no correlation. Whatever it does, my left hand can be whatever on my right. These are also examples of what can be a correlation factor. Consider two variables to compare. Then I say, well, let's do this analysis on my 4 variable I recorded against the signal amplitude I received. I say, this is the correlation, white low, signal against the pressure, not so much correlation as expected. Signal against temperature, quite good correlation, of course, I will try to say. This is about relative humidity, some correlation, but probably not so easy to really understand, or a side effect, or is just some noisy measurement. And then what was the most interesting thing that is rainfall signal, it is almost no correlation. Well, everybody was expecting to see when it rained, everybody knows that the TV tried to fade out. Why this experiment did not show up that behavior? Well, there is a why, of course. Let's try to summarize. Here I have no or very weak relationship with the atmosphere, very weak correlation with humidity, or maybe there is some correlation but probably is buried into the system error. Signal versus temperature is due to the drift of the gain of the LMB. It is more or less 0.1 degrees Celsius. That is more or less what I measured also in a climatic chamber. So probably I was reading right. And see, this is the strange. There is no correlation, but was not what we expected. Let's try to have a look to the punch of data. Here we have the signal level. and here is the rainfall, the red line. The green is the temperature. Here it comes the shower. Temperature drops. Cold wind. The signal starts to fall, but then I read the rain. Here I have a very huge rainfall, but then the peak of the fading is down here, several minutes after. Well, of course, if I cannot find any correlation in that way. Later on, the storm will continue. I have another heavy storm of water here, but then the peaks of the fading is down here, probably 10-15 minutes later on. Of course, if I try to compare red against blue, I found no correlation because things happen at different time. Probably it happened, but not at the same time. Why? Because in fact, I'm measuring, this is the easy picture. I have the satellite very high in the sky. Here there is the storm that is coming, heavy rain, but my house is here. I'm recording the rainfall at this point, not along the signal path. So the heaviest rainfall rate comes usually from showers. Showers are very limited in space, usually, and they move quickly. So what is happening usually is the shower is coming. I'm still under the sun, but the path of the signal is under the shower. So I see the fading here, but they still read 0 here. That is the fact. And the other way around, maybe I have the shower on my head, I get a lot of water on my roof, a lot of reading, but the path signal is almost on the clean again. All that is to explain what I found. That was so probably obvious, but this, when you see pictures and figures, it's start to be exciting to struggle. So that they say, well, let's try to arrange and try to calculate some kind of availability. I compensate all the data against the thermal drift, so I have a new bunch of data, and say, well, if I consider to lose about 20 dB from the average, how much time is along the 1 year is below that threshold? I have more or less 24 minutes every year. I have more than 20 dB of losses. If I say I more or less 12 dB, I have 2 hours and a half every year of losses of signal, and so on. And say, well, I have something. This is for one frequency, one beaming, but I would like to know if we can try to extend, at least roughly, this study to say whatever beaming is in the sky. Of course, the study is very complicated, but I try to say two things. The rainfall normally starts from 5,000, 6,000 meters above our head, more or less. And I took another hypothesis. The rain rate and the drop size are more or less constant from the sky down to the ground. It's not really true, I know, but let's take some simplification, otherwise it will be a terrible mess. If I take as a good statement those two blue ones, I can try to calculate the extra margin I need in sizing my receiving system, consider the elevation of the dish, and how much minutes every year I can accept to lose the signal. In other, how can you read this table and say, I have a satellite 65 degree height in the sky. I can accept no more than 1 hour per year to lose the signal. Okay, this is something in between. Let's say I need probably 6.9 is in between here, 10 dB extra gain on the dish. So if I size in a good sky for 1 meter of this, if I have to ensure that no more than 1 hour per year the satellite will disappear or will not give enough signal noise, I need probably something 5 meter dish, something like that, 10 dB more anyway. That is the problem. If the satellite is not just high in the sky, but is maybe 15 degrees because it's far away, 1 hour is down here, more or less, and it means that they probably need 16, 17 dB extra dish or antenna or receiving capability anyway. And this is the way you can use this data. That maybe is not so important for amateur point of view. It's very important for commercial use when, of course, you pay for a service and you want to know, okay, I pay you for a service. How much time you will be not able to give me such a service? That is the typical question in commercial. And this is the idea as the engineer say, well, I have to guarantee that my customer will not lose any signal for more than that time every year. How big I have to do my receiver. And this is an idea. Or we can approach this problem. This is a graphical perspective of what I said before on the table. And more or less the study ended up with two more questions. I say, what next? For sure there are few interesting points. One for sure is to try to enhance the accuracy of the system, because probably there are several more phenomena that could not put in light that affect the signal path. But of course I need something better than just a rough LNB and a receiver and blah blah blah. I need something better. And also this study was just examining the total energy collected at the ground level. So how much energy I lose during a shower or during some phenomena. But there is nothing about the quality of this energy. It's very easy if you try to listen to with a narrowband receiver to the beacon of the satellite during a shower. You see really like aurora effect or very spread. So probably the energy is not just lower, but it's spreading over a band. And this can affect, furthermore, the capability of a communication channel. That was not taken into this study. Can be a good tips for the next page or next years, because in fact it takes more or less 1 year to set up everything and 1 year of logging, so it's a long term. The other good point for me that is I did almost everything by myself, but I think it's very good to do on a teamwork, because you can have people expert on beaming, someone on antenna, someone in the receiver, someone very nice to write code for the computer. So if we have different companies around the table, it can be done in far better way, these things. But why not? Anyway, try to do it. I should be on the bottom.
So thank you very much.
Welcome. Tell me.
First question and a microphone, please.
I'll let you repeat it. Right.
Go on then.
Doing some work myself with satellites, what we discovered was it was ice crystal size in thunderstorm clouds, and where your signal went through the ice, through the thunderstorm, the base of the thunderstorm, obviously the crystal size varies, and that seemed to alter the signal dramatically from having no signal at all to having quite a good signal as the storm drifted out of the way, so the signal returned.
It's probably the same things I found here.
Yes, it wasn't really rain. We couldn't never tie it down to rain. It was the size of the ice crystals. The bigger the hail crystals, or when the hail got to a specific size of the frequency we were using, that's when it disappeared.
I know this study, for being really scientific, it should keep in under consideration also the kind of fall. If it's ice, if it's snow, size of their drops and whatever, that are far beyond my possibility, of course, at home. But can be a good study for someone within a university, say. Let's say take as a draft, and then let's go deeper.
In this country, we have a service provided by Sky, and they put a tiny little dish up. And they're very susceptible if a thunderstorm sort of passes in the line where the dish is pointing, the signal drops right out.
Anyway, I know.
That drops out with only about 6 dB difference, I suppose. Any other questions?
Yes, I might have missed it. Have you considered variations with time of day?
I saw nothing in particular. There is a continuous oscillation, but it's due to the variation of the temperature, night against day.
The reason I ask is I've got a place in southern Spain, and there's thousands of people down there trying to get BBC on very, very fringes, and they will all swear that it varies. 9 o'clock you don't get BBC One, but you can get Channel 4, and time of day seems to be a key factor that they're noticing. But maybe other factors. The second question is that rain is affected by humidity, air temperature, and atmospheric pressure. And you showed correlation graphs of each of those variables independently. Have you thought or looked at taking account of those three variables in looking at the rain? Because there might be a signal in there which you're missing by not taking account of the other variables, because they're not independent variables, they're dependent variables.
I know they are not independent at all, and the problem is it's not easy to put in light, the correlation. Not with the tools I used. I probably need a better resolution of the data, for sure, and probably also some other data that is not temperature and humidity at the ground level. That is.
I did a bit of medical epidemiology about 20 years ago, and there was a software estimate. Yeah, I did a bit of. It just parallels some medical epidemiology stuff I did about 20 years ago on multivariate analysis, looking at different factors that affect disease. And there was a package we use, SPSS, which seemed to be able to do multivariate analysis on massive pieces of data. There may be just something. There may be information
I appreciate.
There
I mean,
just not picking up.
I just offering what I did, and probably it can. Really everybody can say, well, why not to try to do something better and more? Why not? Okay.
Thank you very much indeed.
Thank you very much.